a nice small round, and everybody probably already knows everybody. So the topic of today is data management and machine learning, or let's say data-centric AI, which is this new exciting direction. We're gonna have a local talk from Stefan Grafberger from the UVA. He's gonna talk about his master thesis work and also the work of his first 1.5 years during the PhD, mlinspect, which is a framework to instrument machine learning pipelines, do some what we call data distribution debugging, and also extract provenance. And after that, Sir will give a talk. He's a professor at ETH. He did his PhD with Chris Ree, won several best paper awards, and he's also publishing both at the machine learning and the data management space. So there's not a lot of people who do this. And he's gonna give us an overview of his research in this direction. And there's also an active collaboration. So we are integrating mlinspect with many of the techniques that SIS group is developing. So yeah, with that, Stefan, feel free to start.
Cool.
Can you see the slides?
Yes, we can.
Okay, nice. So hi and welcome all to my DSD talk. So today I'll talk about our library mlinspect, which is, as Sebastian already said, project that I started from my master thesis and now continue working on. And this is joint work with Paul Gross, Julia Stojanovic, and Sebastian. And during this presentation, I will talk about some of the more technical details of the project and about performance aspects. And if something I talk about isn't clear, please feel free to just interrupt me and ask. So first, let's look at what a machine learning pipeline looks like. So if you look at the box on the right, you see this part that we call the last mile of end-to-end machine learning. And this is the part where a ML model gets trained and evaluated. And typically, this box is what a lot of machine learning research focuses on, and they totally ignore the data preparation. But that model training is only a small part of the overall pipeline, and ML researchers are currently realizing that too, and now initiated a push towards data-centric AI to address this. And if you look at the left, you see what happens in a ML pipeline before that step. So first we have data from typically several heterogeneous data sources. This can be, for example, data lakes, log files, crawls, and APIs. And then we have some data preparation stages. We need to integrate and clean the data, turn the relational data into matrix data that can then be fed into an ML model. And then the final ML model is trained. And there are a large number of different frameworks and tools that get used for this, as you can see in the bottom of the image. And the main issue is that there are many problems that can occur not just during the model training, but also during the data preparation. Let me give you a few exemplary issues that can occur in these pipelines. So for example, if you have labeling errors or data quality problems in the input data, they might propagate to train and test data. If experimentation is not done carefully, there might be data leakage between train and test set. And also many models require the features of the data to be normalized and don't work well if that's not the case. And there might be data representation bugs. For example, data from certain groups might be filtered out by accident. And all of these issues are hard to catch, can produce bias, or might negatively affect the performance of the ML model. And that's why I think we should automate assistance for these kind of issues as much as possible. And one big reason why these issues still exist is there's typically a gap between ML research and ML usage in practice. So from the perspective of a university lab, you usually already have a single integrated benchmark data set that you use that is already clean and well understood. And then an ML expert writes a Jupyter notebook to train an ML model. But in production environments, this looks more like in the image we looked at earlier. So there are many heterogeneous data sources. It requires a complex pipeline to integrate and clean the data. And often the people working on this don't have a strong background in ML or statistics. But then if you look for it, you notice that even many experts and big companies make these mistakes too. And why is it hard to build tools to inspect machine learning pipelines and to detect these types of issues? So in relational databases, we have the relational algebra. This makes things like query optimization much easier. We also already know exactly how to compute different types of provenance, for example, Y provenance. And in machine learning pipelines, we don't have an abstraction like the relational algebra. And pipelines are built using different libraries like Spark, Pandas, and scikit-learn. And then at different pipeline stages, different data representation formats are used, like pandas data frames, NumPy arrays, sparse matrices, and so on. And there are different ways to approach this problem. So one is to invent a new system in which everything is easy, and then we can rewrite all code using this new system. So system ML is an example for such a system, but the problem with this general approaches is that rewriting existing code, unfortunately, isn't very realistic in many cases. So another option is to manually annotate and instrument existing code. So current experiment tracking tools like MLflow use this approach. So users have to annotate their code with stuff like logging statements. But unfortunately, in reality, many practitioners, or most practitioners, do not take the time to add these annotations to their pipelines. So what we decided to do is to integrate our system with the existing data science landscape. And it's actually more doable than you would think, because our observation was that different popular machine learning libraries use very similar abstractions. So pandas and Spark mostly use relational operations. Scikit-learn, Spark ML, and TensorFlow Transform mostly rely on something called estimator transformer pipelines, which are a composable way to declaratively specify pipelines. And by basing our system on these abstractions, we are able to handle a large variety of libraries. So to give you a more concrete idea of what type of use cases we are interested in when starting to work on mlinspect, an example for you. So here's an example pipeline with healthcare data. And the pipeline is supposed to predict patients with a higher medical risk than average. And this pipeline is written using pandas and scikit-learn. And we load two CSV files, join them, and do some pre-processing, like projections and selections. And then we use a scikit-learn pipeline for missing value imputation and featureization. Then we use the data to train a neural network. But even in this simple pipeline, there are many issues that can occur. So for example, the join, the selection, the imputation might change the proportions of groups in the data. In this issue 2, we remove the age group column, but it might be required for fairness analysis later during the pipeline. And then we also use race as a feature, which might be illegal. And then we also use a word-to-vec transformer using the names, but then embedding vectors may not be available for very rare names. And now the question, can we automatically hint data scientists about problematic operations? So in software engineering, we have these types of code inspections. So modern IDEs like IntelliJ can automatically detect certain types of issues. You can see an example in the image on the right. It's a bit small, but what happens there is we are trying to access the value of an optional without checking first whether that optional might be null. And then IntelliJ immediately warns us about this potential issue and we can fix it. And our goal was to build this kind of automatic issue detection for machine learning pipelines. And to detect these kind of issues, we need to start by first extracting an abstract representation of these pipelines. So let's look at the directed acyclic graph here, the stack on the right side. So here we have first normal relational operations like joins and projections, then a train test split, and in the different transformers as they get applied to different columns. And in the end, there's a concatenation, and then we feed the training data and the labels to the neural network. And then with this abstract representation, detecting these issues we have on the left side is much easier. So for each issue, we can pinpoint a specific operator in the DAG we need to look at. And this extracted DAG you saw just now is the basis for our library mlinspect. We use it to instrument machine learning preprocessing code with custom inspections. And for this, we don't require users to change their code in any way. And they have a declarative pipeline using pandas and scikit-learn. They can just import their code directly. In the image on the top right shows the API. Users really only have to specify a pipeline file and specify which inspections to apply. And this code snippet here detects all the example issues we listed in the pipeline picture before. And the basis for this inspection mechanism is to allow the propagation of annotations for each row through the pipeline. And we provide several inspections as part of mlinspect. And these include Y provenance tracking, sampling of intermediate outputs, and tests for distribution changes of protected groups. But you can also write your own inspections easily. So here are some example inspections in detail. So here we have an inspection that can track Y provenance which can help to track specific rows through the pipeline. So here we have a really small example. We have two tables that we join on the social security number, and then we do a projection. And we can do lineage checking by generating unique identifiers in the beginning for each row. And then we can just propagate them through the different operators. Another example is the change detection for the proportions of protected groups. So here we have a small code snippet that filters the data for people from a specific county. And after each operator, we can compute histograms. So here we compute, consider the age group. And then before the selection, we have an equal number of rows with age group 60 and 20. But after the filter, we compute the histograms again, and then we have a 63% of rows with age group 60, because there was some correlation in the data. And these are really easy to miss. So in the end, our checks can then look at these histogram changes and decide whether to alert the user about a potential issue. And when we have a projection or a one-hot encoder that transforms that age group value, then we can also add the age group as an annotation to that column and use the same annotation propagation mechanism like in the lineage inspection.
Stefan, can I maybe ask a quick question here?
Yep.
How do you determine whether there is indeed a problem in the distribution or whether the distribution isn't representative?
So far, we only have a very simple baseline approach that's easy to configure. So basically, the user can just input some relative change that is considered okay or not. So for example, if before we have 50% of rows are from age group 20, but after only 33, then we can compute the relative difference, and then we can just check that against some threshold. And then if the distribution changes because of a filter like that, that approach is particularly sensitive to minority groups, because the distribution, the relative, the percentage changes more drastically.
Okay, thanks.
Yeah, but but this answer kind of means that for people, for the machine learning practitioners that you want to help, there is still some way to go, because I mean, all kinds of statistics may be changing, but if you're not aware of the importance of that, you probably will still miss it.
Yeah, for sure. Also, users have to specify which columns are considered sensitive. So in this case, it's the age group, but then users still have to be aware that there can be issues concerning specific columns.
Mm-hmm. Yeah.
But then I think the goal of such a tool can't really be to reliably find all issues. It's just as a tool that can generate potential issues or warnings, and then you can look into that, but it can't automatically completely fix them. Okay, should I continue?
Sure.
Okay, so we also allow users to implement their own inspections. So the interface can be seen here on the top right. And the inspections we saw earlier also use the same interface. So the inspections have two functions. So visit op for visiting an operator, and op annotation after visit. And the idea is that these inspections process tag nodes and the data flowing through them one by one. So you might know the visitor pattern from software engineering. And let's look at this visit operator function first. So the inspection gets an op context with information like which kind of operator do we have here currently, a join or a selection, whatever. And then it also gets an iterator over input-output pairs. And then it returns an iterator with annotations for the output rows. And in the second image on the right, you see how these visit operator functions are typically implemented. So they basically all use a for loop over the input-output annotation tuples, and then just yield the resulting annotations. And then the second inspection function, this op annotation after visit, gets called once the first function processed all input rows. And then it can be used to annotate the currently processed tag nodes with something. So for example, the inspection that we use to detect distribution changes annotates the DAG nodes with histograms of the protected groups. And then because we implement the inspections with this iterator approach, we can use loop fusion when we have multiple inspections to apply. So basically, we only need to do a single scan over the input-output annotation tuples of each operator. And then we call these inspection wizard op functions repeatedly to process each of these rows. And if the inspections only use a limited time to process each row, and if the annotations have a fixed size limit, then the runtime overhead of this inspection mechanism is linear in the number of input and output records. And now that you saw what mlinspect is and what our inspections are, now let's look at how mlinspect works on a high level and how we can support unmodified programs. So as you saw, the initial input is really only the executable user code and a set of inspections and checks to execute. So checks are basically just wrappers for inspections that consist of a set of required inspections and then have a simple assertion function that just evaluates the output of these inspections. Now let's go over the different required steps. So we start by finding out which inspections we need to run. So different checks require different inspections. And then we start with instrumenting the user code. So we rework the instrumentation process repeatedly, for example, to add support for control flow. If you take a look at our initial CIDR paper, the instrumentation process back then worked very differently. But then the main approach we use now is called monkey patching. So Python allows us to override arbitrary functions from arbitrary libraries with our own functions. So basically, we replace functions like the merge function in pandas with our own patched version of the original function. And the patched merge function internally calls the old merge function, but also executes these inspections. And to actually do the monkey patching, we start by using the Python parser first to get the abstract syntax tree of the pipeline. And then, as you can see in the image on the top right, can add the monkey patch import and the monkey patching calls to AST, the user program. And that's that. And then also mlinspect has a feature to pinpoint the exact code location of individual operators. And to get that information, we also can optionally insert callback functions to all function calls in the AST. So you can see this in the second image on the right, the set code reference function call. And these callback functions give us the precise code location, so the line number, column offset, end line number, and end column offset for each original function call. And because this has some performance implications, the step is optional, but these callback functions only need to assign 4 variables. So they are cheap enough in most situations. So now on to the third step. Now that we made all of these modifications to the AST, can then just compile and execute the AST. And during the execution, the patched version of these functions like pandas merge get executed. And in these patched functions, we have the mapping from function call to DAG operator type. So we know that a merge call, for example, corresponds to a join in the DAG. And then we can start by adding the new join node to the DAG. And then we call in this case, a pandas backend. We have library-specific backends to execute our inspections for the join node and give it the input and output of the join. And then we can store the resulting annotations from the inspections in a new private hidden attribute in the pandas data frame object, along with some identifier for the DAG node that corresponds to that function call. And then after executing the pipeline, we have the DAG and the inspection results for different DAG nodes. And in the end, we only need to evaluate the checks on the inspection results and we're done. And here you can see how this monkey patching works. So here we have an exemplary monkey patch for the scikit-learn function label binarize, which takes a vector with different labels and then outputs a vector with Boolean values. And for the monkey patching, we use the Python library Gorilla that simplifies the writing of monkey patches a bit. So here you can see these annotations, Gorilla name and Gorilla patches, and they tell Gorilla that this execute label binaries function that we define here, probably, I'm not sure if you can see my cursor, that this should replace the original label binarize function. But in this patched version of the function, we still have access to the original version of label binarize, and we can use that to create a patched version of the function. So here we have this. So here in this op context line, you can see we have this mapping to a DAG operator type. In this case, it's a projection that modifies column values. And then we want to insert the node in the DAG, but for that, we first need to know the parents of the current operator in the DAG under construction. So as I mentioned before, to do this mapping, we save in each data frame like object a hidden attribute which DAG node the current value originates from. So we can just look at the inputs to label binaries. In this case, it's one data frame, and look at this patched mlinspect attribute and find the ID of the parent DAG node. And then you can execute the inspections. So here, for this, we use library-specific backends. In this case, we have a scikit-learn backend. And here we see that we call this original function call, result equals original. And it's wrapped by these backend functions, before call and after call. And with these backend functions, the backend gets to see the input and output of the original label binaries function and can call the inspections. And then once we executed the inspections, we can add the new node and the inspection results to the DAG. And now to some more details about the inspection performance. So in the initial version of mlinspect, we implemented inspections via fork comprehensions on iterators. This is what I showed you earlier. But this approach also meant that we had performance critical code. So the inspection data processing functions that were entirely implemented in Python, which is a very slow programming language compared to low-level programming languages like C++ or Rust. So to improve the performance further, started working on moving the computation of inspections into more efficient data processing systems. But this is still in an experimental state and work in progress. And the idea is that for each patch function, we generate one small query plan for joint execution of the user operation and our inspections. And then we can execute that small query plan, some system like pandas. Ideally, we switch to a faster system like DuckDB in the future that allows zero-copy data transfer from and to Python, which is really important for this. And then here we have an example of such an inspection query plan, pandas join and the corresponding execution of annotations. And in this case, we look at the histogram inspection and the lineage inspection, and then we generate this query plan. So let's take a look at it. So we have this left input and right input. So these are the two data frames we want to join. And we also have annotations for each of these. And we start by concatenating them. And then we have the original join that was specified by the user. And we just executed original join. And then we have this projection and rename step. So there we basically just name the columns according to some conventions. So our inspections can work with them. And then we have this map function for the lineage inspection. So in this case, basically just combines the lineage annotations from both join input sites. And then for the histogram inspection, we want to forward propagate sensitive attribute like age group. And for that, we don't need to do anything. We just rename that according to some naming conventions. And then in the end, we want to generate 4 different outputs. So first, the output the user expects from his join operation. So for that, we just need to do a projection. Then we want to have the annotations for the output rows for both of our inspections. And then finally, the histogram inspection and the lineage inspection also annotate the DAG node with something. So in the case of the histogram inspection, we use a count aggregation to compute these histograms. In the case of the lineage inspection, we materialize like selected rows and their lineage. And here you can see the performance plots for some function calls with the overhead of our inspection execution. So we have 3 operations we look at here. The pandas function drop null that drops all rows that contain null values. The pandas merge function and the scikit-learn one-hot encoder. So selection, a join, and a map function. And we test the instrumentation of this function with different numbers of rows and look at the resulting runtime. We compare the runtime of the original function without instrumentation, the runtime with instrumentation with 2 different inspections, the histogram inspection and the lineage inspection that you already know. And for these inspections, we compare the Python iterator-based implementation with the optimized implementation, where we execute the inspection query plan with pandas. But if you use DuckDB for this, this would be, of course, even faster. And you can see that the iterator-based Python implementation has a much higher overhead than the optimized implementation, but that it scales linearly with the number of rows and has an overhead that's still low enough to probably not matter in many cases if it's a pipeline where you also do expensive ML model training, because that typically dominates the pipeline execution time. And the optimized inspections are much faster. So in the case of drop null and the one-hot encoding, the optimized inspections do not need to do a lot. So the most noticeable overhead for the lineage inspection in the merge function, and this is mainly because of the step that combines the provenance annotations from both join sites. And then while this optimized execution is still work in progress, it shows that the performance overhead can be reduced to a level where it is an option in almost all situations to just always execute your pipeline with mlinspect instead of with plain Python. And now to some information about ongoing and future work. So one big to-do I already mentioned is finishing this optimized inspection execution. And the second thing we started is using mlinspect as a runtime to implement different systems for different use cases on top of it. So in the Argus project, we use it to develop a tool for automatically screening machine learning pipelines, which can be used as part of continuous integration pipelines. And it has features like the computation of fairness metrics, storing provenance information, and then also computing approximate Shapley values for input rows, which is really cool. But I think we might hear more about that during the second talk today. And finally, we are working on enabling more advanced ML pipeline analysis that requires automatic rewriting of ML pipelines. So our goal with mlinspect was to build a tool that can instrument and execute your ML pipelines without any observable differences in pipeline behavior, and to really only look at a single execution of this pipeline and try to do everything by just watching that one execution. But then, for example, when you want to test the robustness of your ML pipeline against different types of data errors, you need to actively rewrite the input pipeline and test many different pipeline variants. And the project is still in an early stage, but if you're interested in more details, I will present our initial ideas at the Beam workshop at SIGMOD in 2 weeks. And then in summary, mlinspect is a general runtime for ML pipeline analysis and is open source. And if you're interested in details or more code examples, you can just look at the GitHub repository and the documentation there. And also, I think it's important to reiterate mlinspect's main limitation. So it really only works for declaratively written ML pipelines, where we understand the semantics of operations. And finally, if you want to learn more about my research, feel free to visit my website. And then thanks for your attention. I'm happy to answer any questions you might have.